Okay, so let's continue with example 3. Now, again, we are given a weak form of the problem, or let's say. So it is, let me highlight it. So this is my weak form. For a problem, it is AE dw dx du dx, and integration from 0 to 2 minus 0 to 2 10w ax dx. So this is the source term, and minus 10wa at x is equal to 2. So 10 is the traction, so prescribed stress, for example. And we are asked for the solution of this problem. Now we are told that obtain the solution to the weak form given above by using the following trial solutions and the weight functions of the form. Now here we have a new definition, trial solution. So this is my trial solution. Basically, this function approximates the solution. We don't know whether this the solution has such kind is similar to this expression. Let's say this type of function can whether the solution is such a function or not, but we assume that we try to approximate the solution, and therefore we call it trial function. This function is called trial function. Okay, and we are given the weight function. Certainly here, alpha 0 and alpha 1 are the coefficients. Beta 0 and beta 1 are the coefficients. They are constants. Okay, so let's continue. So remember that, so just take e 10 to the power minus 10 to the power 5. And of course, we can say that at x is equal to 0, beta is equal to 0, because at the prescribed displacement, so where it is x is equal to 0, this weight function has to be 0. Therefore, from w0 has to be equal to 0, therefore beta 0 is 0. So this coefficient will vanish. Okay. Now, this is what we can say about the beta 0. Of course, we are given the prescribed displacement. Let's say that at x is equal to 0, displacement is 10 to the power minus 4. Therefore, from here, we can easily say that alpha 0 is 10 to the power minus 4. Indeed, as a result, what we are going to solve is these functions. So ux 10 to the power minus 4 plus alpha 1x, wx is equal to beta 1x. So this is my weight function, and this is my trial solution. Now, I need to calculate the derivative of the trial solution and weight function, because I'm going to submit these values into the weak form. If I take the derivative of this value, I'm going to get what I get is du dx has to be equal to alpha 1, and the w dx has to be equal to beta 1. Now, after substituting all these things into the weak form, this approximation, what I'm going to get is from 0 to 2 beta 1 alpha 1 e dx minus 0 to 2 beta 1 x 10 dx minus beta 1 x 10 at x is equal to 2. And this expression has to be equal to 0. Now I'm going to solve this expression and I will find the beta 1 and alpha 1 from here. So if I integrate this expression, for example, it is going to be from 0 to 2x, and this will give me x squared divided by 2 from 0 to 2, and this will give me 20 beta 1. If I take out the beta 1 outside the parentheses, what I'm going to get is beta 1 multiplied by 2 alpha 1 multiplied by e minus 20 minus 20, and this has to be equal to 0. Now here is the critical point. In order this expression to be 0, the expression inside the parentheses has to be equal to 0. So this is the only way. So remember that the weight function is arbitrary and we can choose any function. Therefore, beta 1 can take any value. As a result, for any value of the beta 1, this expression has to be equal to 0. And the only way that this expression is equal to 0, the expression inside the parentheses has to be equal to 0. So from here, I can easily obtain that 2 alpha 1 e is equal to 40. From here, alpha 1 is equal to 20 divided by e. So I can easily calculate it, because I can, if I submit 10 to the power 5 in place of e, I will obtain 2 10 to the power minus 4 for alpha 1. Now, the exact solution for this expression is 10 to the power minus 4 multiplied by 1 plus 3x minus x cubed divided by 6. And sigma, the stress for this problem, is 10 multiplied by 3 minus x squared divided by 2. So the du dx multiplied by e. Okay. Now let's continue with the same example. And let's use another trial function and weight function. Now in this case, we have the trial solution, parabolic. So second order, we approximate the solution, the displacement field, by a second order polynomial. We can use any function indeed. And again, we use a similar type of weight function, wx as a quadratic function as well. So it is alpha 0 plus alpha 1x plus alpha 2x squared, and the wx is equal to beta 0 plus beta 1x plus beta 2x squared. I know that alpha 0 is equal to 10 to the power minus 4 because I substitute 0 in place of x. So these terms, these two terms will vanish. And it will be the same for w. These terms will vanish as well. And as a result, since the weight at the essential boundary when x is equal to 0 has to be equal to 0, from here I can find that beta 0 is equal to 0 and alpha 0 is 10 to the power minus 4. Okay, now Next thing is to substitute these two functions into the weak form. Of course, I need to take the derivatives of these values, these functions. So the derivatives are alpha 1 plus alpha 2 divided by 2x for u, and w is beta 1 plus beta 2 divided by 2. Sorry, 2 beta 2x, and this is 2 alpha 2x. So these are the derivatives. So beta 1 plus 2 beta 2x is the derivative of the w, and this is the derivative of the u with respect to x, and then I multiply it with e, and then I will integrate it. Identically, I have the distributed loads or source terms. In other words, now I have the derivative of, I have the weight function multiplied. So beta 0 is 0. It is beta 1x plus beta 2x squared multiplied with 10. And I integrate it over from 0 to 2. So identically, I have the boundary conditions here, the traction boundary condition. It is beta 1x plus beta 2x squared multiplied by 10 at x is equal to 2. So I replace 2 in place of x in this equation. Now, if I do the calculation and collect the terms, and take out the beta 1 and beta 2 outside the parentheses, what I'm going to get is these two expressions. So it is beta 1 e 2 alpha 1 plus 4 alpha 2 minus 40 plus beta 2 multiplied by 4 alpha 1 plus 32 alpha 2 divided by 3 multiplied by e minus 300 divided by 3, and this expression has to be equal to 0. Now, here is the point. We know that weight is arbitrary. So, in order this expression to be arbitrary, we can choose any function for weight, right? And the only way that this is satisfied is beta 1 and beta 2. Basically, this means that beta 1 and beta 2 can take any value, even though they are constants, but it can take any value. Now, when beta 1 and beta 2 can take any value, the only way that this expression is to be 0, these two expressions has to be 0. So beta 1 multiplied by e 2 alpha 1 plus 4 alpha 2 minus 40 has to be 0, and beta 2 multiplied by 4 alpha 1 plus 32 alpha 2 divided by 3 multiplied by e minus 300 divided by 3 has to be equal to 0 independently. So this is the only way that this expression is satisfied. Now here is another point. Since beta 1 and beta 2 can take any value, certainly the expressions inside the parentheses has to be equal to 0. This is what it means. So from here, since this has to be equal to this has to be equal to 0, and this has to be equal to 0. This basically gives us two equations with two unknowns. So alpha 1 and alpha 2 are the unknowns here. And in matrix form, we can write this pair of equations like this. So 2, 4 multiplied by E here, alpha 1 and alpha 2, right? So if you multiply this row with this vector of unknowns, you are going to get 2 alpha 1 and 4 alpha 2. Then it is the same for the second equation. So remember that 4 comes from so it is like this. 2 comes from here, 4 comes from here, 4 comes from here, and 32 divided by 3 comes from here, and certainly 40 comes from here, and 300 divided by 3 comes from here. Now I have a pair of equations with two unknowns. Now I need to solve this equations. If I solve this set of equations, what I'm going to get is alpha 1 is equal to 3 10 to the power minus 4, and alpha 2 is equal to minus 0.5 10 to the power minus 4. So from here I can easily write the approximated displacement by a quadratic function. It is 10 to the power minus 4 multiplied by 1 plus 3x minus 0.5x squared, and stress is then 10 multiplied by 3 minus x. Certainly the approximation makes some error. Now let's look at the error in displacement. So remember that our domain varies from 0 to 2, and this is our exact solution. When I use a linear trial function, my displacement, approximated displacement, is this one. Now if I use a quadratic trial solution, my approximated displacement is this one. Certainly, whereas the exact value for the displacement is this. Now, as you see, as I increase the order of approximation trial solution, the difference between the exact solution and the approximated solution decreases. As you see here, for example, this is the error. Here, for example, this is the error. Whereas for the linear case, error is much larger. And certainly, of course, at the prescribed displacement, the error is 0 on the boundaries. So this is why we call this is weak in this sense. I mean, this is why we say that this is a weak form of the problem. This is because strong solution or strong form will give us the exact solution in general. In the weak sense, we are approximating the solution. So there is a certain amount of error and we are just pulling the solution towards the exact one. So let's look at the stress. Now, if we look at the stress, this is the dashed line is our exact value, exact solution of the problem. Now, in the linear case, as you see, the stress is constant over the domain. Sigma is constant, and it's 20. But for the quadratic approximation, as you see, it linearly changes from 30 to some value. Again, at the boundaries, you have zero error for the stress. But within the domain, for example, for a particular case, this is the error, and the error is changing. But certainly, the total error in the quadratic case is much lower than the linear case.